Hello, students. Welcome back to Tuition Masters. And today we are going to start with the next chapter, which is work and energy. And this is a one shot session for the entire chapter. So let's understand what all things are we going to cover. So in this chapter, we will be understanding about work, which is a concept of work done by constant force, and positive negative work. Even energy and its type by kinetic, potential energy, transformation of energy, and law of conservation of energy. And the last topic, rate of doing work, and under that we will be studying power and commercial unit of energy. So let's get started. So let's understand the first concept of work. Now consider that a boy is throwing a pebble on a table. Okay, now if the boy will throw a pebble, so what will happen for few seconds? It will at a particular distance it will slide. Correct. So can we say that some work is done? Yes, we can say that work is done by what? If the force is applied. If the force is applied on the object and the object is getting displaced, so yes, I can say that work is done. Similarly, another example is, take suppose a person is trying to push a heavy rock, but the rock is not moving only. So is work done over here? No. We will say the work is not done over here because the force is applied. Yes, it is true that the force is applied, but displacement is not taking place. So that's why no work is done over here. So, for a work to be done, there are two conditions to be satisfied. First is there should be a force acted upon the object, and the after applying the force, the object should also move or get displaced. Then only we can say that work has taken place. So let's understand the work done by a constant force. Now, let a constant force F is acting on an object. Let's take I have a force F. Okay, it's acting on an object, and the object gets displaced by a distance S due to the application of force. It's just moving from here to here by the distance S. Okay, due to the application of force. Alright, now the work done by a force acting on any object is equal to the magnitude of the force multiplied by the distance. So this means that work is equals to force multiplied by the displacement. Force is represented by F and displacement is represented by S. So we can say that work is equals to Fs. So this is our first formula. Now, work is equal to force into displacement. What are their SI unit? The SI unit of force is Newton, and for displacement it is meter. So the SI unit is Newton per Newton meter, which is also known as joules. So work, the SI unit of one is joules. Now 1 Newton meter is equal to 1 joule. Alright, and this unit of work, joule, is named in the honor of the English physicist, which is James Prescott Joule. So, on his name, this unit came out. Now, we know that both force and displacement are vector quantities. Yes, but what about work? So, let's understand that a boy is having two boxes. He pulls them into different directions, opposite directions. Now, the boxes are pushed in the same force and they cover the same distance as well. Correct. Let's say that the force applied is 1 Newton and the box moved by 1 meter. So, work will be what? 1 into 1. So, work done will be 1 joules. Correct. So it will be 1 joules. Now the boxes are pushed with the same force and they cover the same distance also. So this means that same work is done in both the directions, right? So since work does not depend on the direction, it is a scalar quantity. Okay, it does require the magnitude, the direction doesn't matters. So work is also a scalar quantity, we got to know. Now, our next, let's solve a question that a force of 5 Newton is acting on an object. The object is displaced through 2 meter in the direction of the force. If the force acts on the object throughout the displacement, then the work done is what? So we have to find the work done. We know work done is what? Force into displacement. So force is given us as 5 and displacement is given us as 2. Correct? So that is nothing but 10 joules. So our option is B. Option number B is the correct option. Next is, let's understand about the positive and negative work. Now, the agent that applies the force is said to be doing the work only. Correct. The agent who is applying the force, he is only doing the work. So while the work is done on the object on which the force is applied. For example, the bull. It is pulling the cart in the bullock cart. The bull is pulling the cart. So the bull is doing the work. Correct. The bull is doing the work on the cart. Right. Now let's take an example that a boy is applying a force of 10 Newton. Okay, is applying a force of 10 Newton on a box of 1 kg. Okay, to lift it from the ground to a height of 3 meter. To a height of 3 meter, 1 kg box, the boy is applying a force of 10 Newton. So what is the work done here? We can say that the force is given to us as 10 Newton and the displacement means how much what is the height, that is nothing but 3. So what can I say about work will be nothing but 30 joules. Correct. So 30 joules work he did. Now, this is the gravitational force which is acting opposite direction of the displacement. It is acting opposite to the direction. What? The gravitational force. So, since the force is opposite to the motion, thus the acceleration will be negative. So, force is what we know, it is m into g, which is 1 into minus 10 we will do. So, we will get us what? Minus 10 Newton. So the force come out to be negative because the acceleration is also negative. So if the displacement is along the direction of the applied force, then the work will be positive. But if the displacement is opposite to the direction of force, then the work will be negative. So force and displacement, if they are both in same direction, so it will be positive. And if they both are in different direction, it will be negative. So here is how we identify. So let's do it with a question. Reason out whether the work is done or not in the following case. You have to identify if work is done or not. First question is a boy swimming in a pond. So while we know that while swimming our hands also move, correct, legs also move, we have to move ahead, correct. So there is a force also, correct, there is a force also. So for the as if there is a force, so there will be some displacement also. So in the first case we can say yes, that work is done. Now, in the second case, we have that food grains are getting dried in the sun. The food grains, they are not moving, right? When the sun rays are coming, they are not moving here and there. Correct. So, there is no force applied, no work is done over here. So, that's why no work is done in the second case. And here are your solutions also. Our next is a potter lifts a luggage of 15 kg from the ground and raises it to 1.5 meter above the ground. Calculate the work done by the gravitational force. By the gravitational force we have to do. So we know that the mass of the luggage is given to us as 15 kg. Displacement is 1.5. Now we know that gravitational force act in the opposite displacement, correct, it will be in opposite direction. So we can say that the gravitational force will be minus 10 meter per second square, correct. Now we also know that the work is nothing but force into displacement, and force can be even written as m into g. So m here is the mass, which is 15, into g the gravitational force, which is minus 10, and multiplied by 1.5. And when we will calculate this, we will get it as minus 225 kg meter per second square, correct, and this meter of the 1.5 also, right, and that will give us nothing but 225 nm, which is minus 225 joules. Just conversion is there, so we get that it is minus 225 joules. So the work done by gravitational force is negative 225 joules. So here is your solution. Now let's understand about energy. Now, in general, we say that energy is nothing but the capability of doing work. So, for doing work, energy is required. So, the energy possessed by an object, it can be measured in the terms of capacity to do work. If someone is riding a bicycle, if the person is putting more force, so there will be high energy. If the person is doing slowly, less force, so there will be low energy. Correct. So, what will be the SI unit of energy? SI unit of energy is also joules. Why? Because energy is just nothing but the capacity to do the work. Correct. So, its unit will also be the same as of work. So, it will be joules. Now, energy. We know the work does not have any direction, means it is a scalar quantity. Similarly, energy also don't have any direction. It doesn't matter any direction, that if direction changes, so I will also affect. No. So, energy as well as work both have the same unit. They both are scalar quantities. Now, next is the types of energy. Now, there are few types of energy which are mechanical, under which we study potential and kinetic. Then we have heat energy, chemical energy, electrical energy, light energy, and sound energy. So let's quickly understand all of them. The first one is mechanical energy. First is potential. Potential energy means the energy of an object due to its position or configuration relative to the other objects. Okay, so whenever I'm talking about potential energy, we discuss that the energy of the object is due to its position. Okay, what is its position with respect to the other objects also? Like, if I'm taking an axe and I raise up at some height, correct, I'll take it up at some height, and so the potential energy is there in it, which is then used to cut. So when I take the axe up, so potential energy gets stored, and when I put it down to cut the wood, so it will nicely cut the wood. So that is potential energy. We'll understand more ahead also. Next is kinetic energy. So the energy of an object that possesses due to its motion, that is kinetic energy. So like if I have a moving car, there is a motion, right? The car will move, that is a motion. So when, due to motion, the energy which we get, that is kinetic energy. Moving car, bicycle, train, all of these are the examples of kinetic energy. Next is a flying bird. Where flying bird is what? Kinetic plus potential both. Why? Kinetic energy, but it is flying at some height. So it has potential energy also. Flying bird, when the bird is flying, so that time it has kinetic energy. And flying at some height also, that is potential also. So it means, in short, I can say that birds follow mechanical energy, because mechanical energy is nothing but potential energy plus the kinetic energy. Next are other types of energy, like chemical energy. It is the energy which we store in substances, and it will be released during any chemical reaction. When chemicals we store, okay, in any substance, and then during chemical reactions it will be released. For examples, fuels such as coal, petrol, petroleum. So when we burn this fuel, they release energy in the form of heat and light. So heat and light will be produced, that is also an energy. So heat energy, like when we burn fuel, paper, wood. So what will happen? Heat comes out, fire comes out. That also becomes an heat energy only. Next is light energy. So sources of light energy are various, like sun, bulb, lights, candle, lamps. All of this, it helps us to see the world around us. Those are light energy. And sound energy, what? The energy which is produced by the vibrations. Correct. Vibrations, and vibrations are there, we will be able to hear the sound, which will be heard by our ears. So that is also sound energy. and electrical energy that we see every day in our life, in our fans, on the TV connection, then laptops, lights, everywhere electrical energy is there. So the flow of electric charges through the wires and conductors result in energy, which is electrical energy. Now, next part is the kinetic energy. Let's understand about it in detail. So, we saw that the energy due to the motion is called as kinetic energy. Clear. But how do we measure it? Like a flying bird, blowing wind, rotating wheels, all of these are kinetic energy. But how can we measure it? So let's say that we have a car and it's rolling down an inclined plane. Here it is rolling down through this, and it moves, and the block moves, the block as shown in this figure. Okay, now when it is moving, it has kinetic energy. Okay, and by moving the block, it has done some work also. Correct. So now let's consider another case where the car is moving slowly. Okay, in compare, let's take this is case number one, this is case number two. In case number one, it's going fastly, but in case number two, it is going a bit slow. So here the displacement of the box is less. Right here, if it's going fast, it will dash and the box will go ahead. But if it's going slow, so it won't dash, or if dash also, it will be very less. So displacement will be very less. So because the velocity of car in the first case, in this first case at point B was greater, but at this point in B it was not. So with this we know that energy is the ability to do work. So the object that possesses more energy will do more work. So since the displacement of block in this part in case 1 was more, so the work is also done more in case 1 only. So this means that kinetic energy is proportional to velocity also. So this means when the velocity is increasing, so remember that they are directly proportional, means when velocity will increase, kinetic energy will also increase, or the vice versa. When kinetic energy will increase, velocity will also increase. Now let's take another example, that let's take we have a bus and a bicycle, or you can say truck also, truck and a bicycle. So they both are traveling in the same direction and the same velocity. Okay, direction, velocity, both are same. Now what will happen if both of them hit a block? Both of them are hitting the block. The truck will push the block at a longer distance, right? It will dash and it will come somewhere over here, whereas the bicycle did not move. When the bicycle hit the block, it won't move because there is not much of energy, right? So this happens because truck has more mass is more, whereas in bicycle it doesn't have that much of mass, right? So this means if mass increases, so work done is also increased. That means kinetic energy also increase. So this means that next conclusion is kinetic energy is also proportional to the mass of the object. If mass is more, kinetic energy will also be more. So suppose that an object of mass m, okay, mass m is kept at a point A. Now if I apply a force F, okay, from this side if I apply a force F on the object, it will get displaced, that take suppose to point B, and this entire distance considered to be S. Okay, and the final velocity is V. So we have few values over here. So we know that the work done is what? Work done is nothing but force into displacement. So work done on the object is nothing but the kinetic energy due to motion. So work done is nothing but kinetic energy only, which is nothing but force multiplied by the displacement. Simple work. So we can calculate the force using the Newton's second law of motion, which is F is equals to m and a, mass into acceleration. So here let's take this to be equation 1, equation 2. Now from the third equation of motion we will get that v square minus u square is equal to 2as, and s will be what? If we just take the values here and there, v square minus u square divided by 2a. This is our third equation. Now we will substitute the value of F and S from equation 2 and 3 into the equation 1. So what we will get over here is that we will get ma into v square minus u square, which was our equation number 2 and 3. So here a are common, they can be cancelled, and what will I get? I will get nothing but m multiplied by v square minus u square whole divided by 2. So this is what how we calculate kinetic energy. So we know that the initial velocity of the object is u, which is 0, and the kinetic energy possessed by an object of mass m with the uniform velocity v will be 1 by 2 mv square. If the initial velocity is 0, then this will be the case. So again we can conclude that kinetic energy will be again proportional to mass as well as velocity. So I hope this much part is clear. So let's solve a question. An object of mass 15 kg is moving with a uniform velocity of 4 meter per second. So what is the kinetic energy possessed? So we have to find the kinetic energy. So we know that mass given to us is 15 kg and velocity is given to us as 4m by s, means 4 meter per second. Now velocity is given. So what we have to find? We will use the formula that kinetic energy is equals to mv square by 2, that is 15 into 4 square, which is, or we can write 4 into 4 divided by 2. So 2 ones are 2 twos are, we will get it as 15 into 8, which is 120 joules. So 120 joules kinetic energy is possessed over here. So here is the solution. Next is potential energy now. So, potential energy is nothing but it is possessed by the object, correct? By the object, and it is the energy which is there by virtue of its position or configuration. Okay, by the position configuration with the other objects, the potential energy is possessed. Now, when the arrow gets released in archery, when the arrow gets released, it will fly off. Correct? It will fly off immediately because of the potential energy when we stretch it. So potential energy is stored. As soon as we leave it will immediately go. So that is due to potential energy. And then here what happens, that converted that energy, potential energy, when we leave the bow, after leaving the bow, what will happen? It will, the arrow will quickly go ahead due to the conversion of potential energy to kinetic energy. All right. Now, how do we represent it mathematically? Potential energy. So let's consider that a boy is doing some work. Okay, and he is lifting a block. It has the block has mass m, and he raised at a height h. Already raised at a height h. Now we know that force required will be mass into gravity. So the block gets displaced by a distance of h meter. Correct. So when the boy raised the box, it gained some energy, right? It gained some energy. So energy gained by the box is nothing but the work we did on it. So we know that energy is nothing but work done, which is nothing but force into displacement. And if you substitute the value of F and S, we will get that E is equals to F into S, which is nothing but mg into h. What is mgh? M is the mass, g is the gravitation due to gravity, and h is the height. So potential energy is mgh. So we got this from this equation. So let's say that an object of mass 40 kg is raised to a height of 5 meter above the ground. What will be its potential energy? And we have the value of g as 10 meter per second square. So we know that potential energy is nothing but mgh. So we have all the values. M we have it as 40. So we'll write here 40 into g we have it as 10, and into height we have it as 5. So we will get it as nothing but 400 into 5, which is 2000 joules. So the potential energy is 2000 joules. So here is your solution. Now, next question is, find the energy possessed by an object of mass 10 kg when it is at a height 6 meter above the ground. And we have the value of G as 9.8. So, we have the mass is given to us as 10 kg. We know that the displacement or height is 6 meter, and the acceleration due to gravity is also given to us 9.8. So, what we have to do? Nothing. So just calculate again, m into mgh, m into g into h, and when you will calculate that, you will get it as 588 joules. So that is the potential energy possessed. So here is how you are calculating. Now, next is the transformation of energy. How can energy get transformed into different forms? Let's consider hydroelectricity power plant. Okay. Now, water in dams, we store it at a certain height. Why? So that if it is at a certain height, so it will gain some potential energy. Correct. Now, when the gates of a dam are opened, okay, when the gates are open, so potential energy which is stored, that will be converted into potential energy, will be converted into kinetic energy. Correct. When as soon as I open the door of the dam, immediately it will flow due to it is converted to kinetic energy. Then the water will fall on the turbines and it will produce hydroelectricity. Now, the turbines, the water falls on the generator turbine. Now, the turbines will transfer that kinetic energy into electric energy through which we can get hydroelectricity. And in this way, the electricity is generated and we can use it. So, what did you observe here? Kinetic potential energy, which is stored on height, that is there. Then we can look at here, potential energy is there. Then that is converted into kinetic energy. That kinetic energy is then converted into electrical energy. So we can understand how the transformation takes place. Now there can be few more examples, such as if a burning of coal, it is a chemical energy. Okay, chemical energy is stored in the coal, right? When we burn it, it will be converted into heat energy. For example, firewood, how is it obtained? By such process only. Charcoal, how is it processed? By firewood. So chemical energy, when we burn it, it converts into heat energy. So this is again a conversion. Next is torches. What happens now? In the torches I put batteries, so that battery has chemical in it, so that is the chemical energy. Now this chemical energy, when I put it in the torch, it converts into light energy and produces light. So this is one more example. Now, the important topic is the law of conservation of mass. Sorry, conservation of energy. Now, what this is called the law of conservation of. What happens is, according to this law, energy can only be converted from one form to another. We can only convert the energy. You can convert it into chemical to a light energy. You can convert it into potential to kinetic. You can do that, but we cannot create or destroy energy, and the total energy which was there before and after the transformation, they will also remain constant only. If I say that in my potential energy it was, take suppose, 75 joules, if I convert it into kinetic energy, so still it will be 75 joules only, it won't change. So according to the law of conservation of energy we can convert it into different forms, but we cannot create or destroy it. So this was it. Now, example of this is the Newton's cradle. You might have seen this many a times. So if we take this ball, so this ball will go here, that is it. These four balls won't do anything. So when we pull this leftmost ball, we provide potential energy, and when we leave it, the potential energy converts into kinetic energy. Okay, and when this kinetic energy is there, what will happen? The first ball will hit the second ball. The second ball, then the entire energy goes to the second ball. Then the energy is transferred to the second ball itself. then then the second bullet goes to third, fourth, and this one fifth, sorry, yeah, fifth, and then it here it will go and it will go towards this. So this is how the mechanism goes. Next concept is of rate of doing work. Say that we are at the airport and there is heavy trolley baggage. Now there is an old man trying to push and there is a young man also, correct? So what do we say is that we have a young man also, he is able to push the load easily, but old man, he is not able to push easily because he is old, he doesn't have that much energy, right? So both did travel the same distance, both applied the same force also, but still time taken was different for both of them. So let's see another example also, that let's take that two kids, Rahul and Ramesh, they were crossing two ropes, they had equal weights, and they took um the weights also, the rope, everything was same, but Ramesh, he went faster but he went slow. Why? So basically, same force was there, displacement was also same, work was also same, but the rate of doing work differed, the time differed. So basically, in physics, this rate of doing work or the rate of transfer of energy is known as power. This is known as power. That if how much, what is the rate of doing work? That is nothing but power. So, power is nothing but it is defined as the rate of doing work or the rate of transfer of energy. And the formula for power is work divided by time. And the power measures the speed of the work, that is, how fast or slow the work is done. If power is more, the work will also be done faster. Similarly, let's take an example. A machine can do a task in less time, and when we talk about a man, because the machine takes less time because it has more power, right? Similarly, if I take a powerful bike, so it will have more energy and it can go fast. But if I take a bicycle or a scooty, it will take less time because it is not that powerful. So this is the concept about power. Now SI unit of power, we know it is so we know the formula of power is work divided by time. Now work is joule, time is second, that's joule by second, and that joule by second has a special name given as watt. So it was given in the famous of like honor of a famous scientist James Watt. So this watt is denoted by a W. So, 1 watt is the power of an agent which does the work at the rate of 1 joule per second. And remember that 1 kilowatt is equal to 1000 watts, and 1 megawatt is equal to 10 to the power 6 volts. Sorry, watts. So, let's solve a question now. A woman pulls water from a well of 15-meter depth in 15 seconds. If the mass of a bucket is 10 kg, then estimate the power consumed in this process. So, what we know is that a woman is pulling the basket, right? I mean bucket. So, work is how much? Work is nothing but force into the displacement, which is m mg into h, like work we can even write it as mg, which is force, into the h, which is displacement. So m we know the mass is 10, into the gravitational acceleration due to gravity is 10, into the height is what it is given as 15-meter depth, so that has become the displacement. So that gives us what it gives us, 1500 joules. That is the work done. Now, when I talk about power, so power we know is nothing but work divided by time. This means 1500 divided by the time, which is 15. So what will it give? It will give us 100 watts. So 100 watts is the correct answer over here. Our next question is the time required to perform 520 joules 520 joules of work at the rate of 20 volts is how much? So vice versa we have to do here. So we know that power is work divided by time. So time will be how much? Then time will be the opposite. That will also be the work divided by the power. So we know that the work is 520 divided by 20. That is going to give us 26. So 26 seconds is the time in this question. So let's move towards our next topic, which is commercial unit of energy. So we use a lot of electrical appliances in our home and electric energy also, like a television, computer, fan, um, refrigerator. All of these work on the electrical energy, right? Now, and even we pay electricity bill also. Electricity energy, whatever we are using, we consume it and we even pay for it, right? Electricity bills come and we pay for it. But how much electrical energy do we consume? Let's take an example of a refrigerator. Now, you might have seen in your refrigerator that there is such kind of ratings, energy rating, and there are some values written like stars are there. You might have observed that sometimes. Now, let's suppose that the rating is 50 watts. Okay, the rating is given at 50 watts, different on the basis of different kinds of refrigerators. When I say 50 watts, this means the power rating of 50 watt means that the refrigerator in 1 second it takes 50 joules of energy. In 1 second it will consume 50 joules of energy, and it is entirely different for different kind of refrigerators. For example, here also 50 volts, it is going to give 50, it will consume 50 joules per second. 1 second 50 joules, 2 second 100 joules, and that way. And we know that a refrigerator runs 24 hours a day, like entire year it works, correct? We don't switch out for a half day when we switch on. No, it runs continuously 24 hours, right? Now let's try to calculate. Now energy consumed in 1 year will be how much? Power into time, correct? 50 into 24 into 60 into 60 into 365, correct? So that will be the energy. And what is that energy? That is nothing but such a big number it will give us. So this much kind of energy is just used in one refrigerator. You can imagine that. So thus, joule is a small unit, and it is very inconvenient to express our daily consumption of electrical energy in joules. We can't write in joules, no? Okay, that in 1 year you consume this much big number of. No, 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 no. We have to write a shorter unit. We know that 1 kilowatt is 1000 watts. So 1 kilowatt hr is equals to 1000 watts hr. So basically, for a bigger unit of energy called kilowatt hours, it is used to represent large quantities. So this kilowatt hours, we use it for representing larger quantities, as this we got. So we use it for larger quantities. So 1 kilowatt hour is nothing but 1000 watts. Alright, and 1 watt we know is 1 joule per second. So 1 hour is what? 3. We know the 1 hour is 3600 seconds. So 1 kilowatt will be how much? The watts are 1000 multiplied by joules per second multiplied by 3600, correct? So 3600 seconds, so the seconds can be cancelled out. What we will get? We will get it as 3.6 into 10 to the power 6 joules. So 1 kilowatt hour is equals to 3.6 into 10 to the power 6 joules. So let's now again calculate the energy consumed by the refrigerator, but now this time let us use the unit of kilowatt hour. So energy consumed in 1 year, we know it's this big number. So 1 kilowatt, we know 1 kilowatt is almost 3.6 into 10 raised to the power 6 joules. So how much energy is consumed? Energy consumed will be the R number, which was in 1 year in joules, divided by 1 kilowatt. And when we do the calculation, we will get it as 438 kilowatt hour. So this is basically the commercial unit which is even present in our electricity bill. And this electric meter also which we have in our homes, it will measure how much energy is consumed in units of electricity. So let's see a question. An electric bulb of 60 watts is used for 6 hours per day. It is used for 6 hours per day. Calculate the units of electrical energy consumed in one day by the bulb. Now we don't have any. We have to just write the energy in units. Correct. So let's try to do this question. We know that power is given to us as 60 volts. So if I convert it into kilowatts, it will become what? 0.06 kilowatts. Correct? Now time is what? 6 hours is given to us. Now we know energy is nothing but power into the time. So energy is power 0.06 into time, which is 6 hours. Now when I multiply, I will get it as 0.36 kilowatt per hour. I mean kilowatt hour, and that is nothing but we can consider to be 0.36 units as it's given in the question. So that's why we can say that in a day the bulb consumes 0.36 units. We can say this here, the energy consumed is this much. Now let's solve one more question, that is a certain household has consumed 250 units of energy in 1 month. Okay, how now we have to express this energy in joules. So we have to convert this into joules now. So we know that 250 units, I can say that 250 units is nothing but 250 kilowatts hour, like as we did in the last question. Correct. So now 250 into 1000 watts, 1000 watts if I do, and even if I multiply it by 3600, okay, 3600 seconds I'm telling, right? So what I'll get, we will get 9 and 1 2, then 3 4 5 6 7 8. Yes, so these, with this number we are going to get. Correct, we can put comma, so we will get this much amount of joules consumed, but this is a very big number, right? So let's write it in short. So we can write it as 9 into 1 2 3 4 5 6 10 raised to power 8 joules. So B option is our correct option. So thank you so much everyone for watching today's video. I hope it was informative. Don't forget to like, share and comment if you have any doubts. And I'll be seeing in the next video where we're going to discuss about gravitation. So till then, stay tuned and goodbye.